actually just because I didn't tell him the title, so he came up with the title on his own. And actually it's very good, because we don't know much about dark matter, so I guess this is as much as we can say. Something about dark matter. So it's going to be a very introductory talk in the spirit of the coffee meeting, but many of you, probably all of you, are familiar with the concept of dark matter. And actually anybody on the streets, anybody in the world is more or less familiar with dark matter. And I think for the topics of particle physics, dark matter is the most known of them all, which is kind of ironic because it is the less known topic in physics. It's actually a great mystery. We don't know what dark matter is. So today I will start by telling you why we think that there is something in the universe that is called dark matter. And well, there are several ways, several indirect signs that point towards dark matter, but the two that I want to focus on are rotational curves where what was observed in the 70s by Vera Rubin is the velocity of the stars in a spiral galaxy. So you have a galaxy, and you observe how fast the stars are moving as a function of the radius from the center of the galaxy. And if you look at these galaxies, you know, they're very luminous in the center, and then they become less and less luminous towards the outside. So you know that when there is light, there is mass. So you think that most of the mass is actually in the center, and then there is less mass as you go outward towards the larger values of the radius. So what you expect is that the velocity of these stars decreases with the distance from the center, because the gravitational pull from the mass in the center becomes lower and lower. So you would expect something like this. This is what Vera Rubin wanted to observe by looking at these spiral galaxies. But what she actually saw and measured was something like this. So the stars, even far away from the center, were not slowing down. They had a large velocity. Okay. If you interpret this in the usual picture that I just described, it means that the mass is not just in the center, but the mass keeps growing, or I mean, at least there is a constant amount of mass, but we cannot see this mass. We only see the luminous mass in the center. This is why people called this new type of mass dark matter. So it's matter because it has mass, so that's what we are familiar with, the concept of matter and the concept of mass, and it is dark because we cannot see it. So this was this is one of the indirect ways to discover dark matter. The other way is gravitational density. This again comes from the gravitational force. So you see there is a connection between these two methods. They both rely on gravity. So they both rely on the fact that there is some form of mass. And how does gravitational lensing work? So you have an observer here, and you have a star here that emits light. So the observer sees the star because the photons reach the observer, okay, in a straight line. But if there is some mass somewhere along this trajectory, we know that mass, through the gravitational pull, will influence light. because it will curve space-time. So the actual trajectory of the light ray will be different. So you would see the star as if it was coming from a different position over here. So this is called gravitational lensing because the space-time deformation acts as a lens and deviates the light rays. So with this method, and with very accurate observations and statistical methods, we can actually map the distribution of dark matter in the universe around galaxies, around dwarf galaxies at different scales, and we can actually draw a three-dimensional density map of the dark matter halos or galaxies out there. So we know that there is some form of matter that we cannot observe because it does not emit any sort of light, and we call it dark matter. So this is how dark matter was discovered, or in other words, why we think there is dark matter. And if we take all the data that we have about cosmology, about the history of the universe, we can actually now draw a pie chart of the content of the universe, the so-called energy content of the universe. If you take a big box, billion light years wide, and you put, you just count how much energy there is inside, how much energy there is in the universe, and then you try to classify this type of energy, you actually come up with a pie chart like this, where this is what we are. We are 4% of this energy content. And by we, I mean the particles that we know of. So all the stars that are made of nuclei and photons, all the intergalactic gas, they're just 4% of the whole energy content of the universe. Then you have another piece of the pie here, about 23% or 26%. This is dark matter. So this is something that has mass, but that we don't know anything about, other than it has mass. Okay. And then there is dark energy, which is something we use to describe our cosmological equations, but again, we don't know what it is. We just know that it is not mass. It's just some form of energy. So it is counted in this pie chart as energy. Now, if you just count the amount of mass, more than 80% of the mass in the universe is not us, it's something else. So we are not very important at all. The most important mass is dark matter. And I guess that's why they started all those Star Wars movies. Okay, so now you know why we think there is dark matter out there. But I actually want to focus on a very specific type of dark matter, which is particle dark matter. So let me assume, since I am a particle physicist, let me assume that dark matter is a particle. Even with this assumption, we still know nothing about dark matter. Okay? So it is not, I'm not actually restricting myself too much. So dark matter is a particle, or many particles, or some sort of particle, because we know what particles are, so we know how to describe them. And so we can come up with some theory for dark matter. Okay, if we come up with a theory of dark matter, how are we going to actually detect dark matter? Because we still don't know what it is. So there are three ways to detect dark matter, or this type of particle dark matter. There is direct detection, and as the word says, direct. This is basically what you would do in an experiment like grids, or like a beam experiment. So you just build a detector that observes dark matter. Okay, That's the difficult part, of course. But what would be the process to directly detect dark matter? So you imagine you have a dark matter particle. Again, I said we're talking about particle dark matter. And then you have a standard model particle, or a particle that you're familiar with, that you know. For example, a neutron, a proton, an electron, something in the standard model. And these two guys, they collide, because dark matter is everywhere around us. Okay, we just had those gravitational probes that tell us there is dark matter just around us, and Earth is actually moving through dark matter. So at some point, a dark matter particle might just come in and hit a standard model particle. And then the recoil of this reaction can be measured. Now, again, dark matter is invisible to our instruments. So what you would see is this guy will be different from what it was before. So what you measure in these direct detection experiments is the recoil energy that comes from this impact with a dark matter particle. Now, we haven't seen it yet, and we have many of these direct detection experiments. Okay, so that means this interaction here must be very, very tiny. Okay, so in order to actually see something like this, you need many, many, many standard model particles, and that's why the detectors that you build are enormous. They're usually underground to remove all the possible backgrounds that is still standard model. You only want to keep dark matter interactions. And then they have tons of, for example, liquid xenon or some other heavy nuclei that can be hit by a dark matter particle. So this is the first way. The second way is indirect detection. In indirect detection, you basically take, and again, the same diagram, because this is how we know particles interact with each other, but now you turn it sideways. So in indirect detection, you have a dark matter particle and another dark matter particle that are out there, and they interact with each other and create standard model particles. So now you have standard model particles coming out of nowhere. Okay. So if you detect something with a specific energy and you don't know where it came from, it could come from this type of interaction. Again, you're not observing this part, you're only observing this part here at the end. So this is why it's called indirect detection. And these are the searches that you do, for example, with cosmic rays or gamma ray burns. Some exotic sources out there in the universe are producing standard model particles. And if you see some anomaly from what you know are this process behave, then you can say that you have observed some new form of matter that interacts with the standard model. And then there is the third way to rotate this diagram, which is collider experiments, where you produce dark matter. Okay, you don't wait for dark matter to do something, you actually make it. Now you have standard model particles on this side, you collide them at some very high energy, and what you produce is dark matter. So now, the final product of this scattering process is dark matter, but again, you cannot observe dark matter with the instruments that you have. So you will observe some missing energy. So you will have a violation of the energy conservation. You know that there is some energy going in, but then you don't see particles coming out. You see some missing energy. So this is missing energy, or is a signature of a dark matter particle production in collider experiments. So these are the three main ways to look for dark matter with our instruments on Earth or with satellites. Okay. As you probably know, we have not observed dark matter yet. But what I want to tell you is that this all these three types of searches depend on the assumption that you are making about dark matter. Because you need to assume something. Well, you're already assuming that you know that these processes are taking place. But then you need to assume something about this interaction. For example, why do you think that there is such an interaction? Maybe there isn't. If there is no interaction like this, then there is no way you can do any of these three if you don't have this interaction in the middle. So if the only interaction that dark matter has is gravitational, right, then you are not able to use these three methods. What you can do, though, is to still observe astrophysical objects to infer some properties about dark matter by simply looking at how gravity responds to the presence of dark matter. Okay. So once you know how to look for dark matter, you need to assume something else in order to predict what exactly are the signatures in your experiments. And that means you have to actually be a little bit more specific than just particle dark matter. And a specific type of dark matter that I want to talk about, and which is what I work on, is called composite dark matter. And this will be the last part of my introduction, is composite dark matter. First of all, as I said, we don't know much about dark matter. For example, we don't know what the mass of dark matter is. We know it's non-zero, okay, because there are interactions with gravity. But we don't know exactly what is the mass. So if this is the mass axis, what we know is that dark matter has to be bigger than 10 to the minus 22 electron volt. This is very tiny, right? This is the proton mass, more or less. Here you have the Planck scale. And then here there is an upper bound that is more or less 30 times the solar mass. So you have many decades of energy, of mass, to explore. And this is just for particle dark matter. So where do you start? How are you going to look for dark matter if you don't even know what the mass is? And different mass ranges behave very differently in terms of interactions, for example. So what people in this field do, they typically refer to the lamppost story. So imagine it's night, you lost your keys, and you are under a lamppost. Okay, so there is light, and you're looking for your keys under the light. And then somebody comes along and says, why are you looking for your keys under the light? Maybe you lost them somewhere else. Yeah, but here at least I can look. So this is the lamppost approach, where you need to have a lamppost, and then you can look. Because if it's dark everywhere, you don't even know what you're doing. So you typically look for a lamppost. Okay, you say, okay, now my light is shining over here, and I know how to look for things that are over here. For example, you can design experiments that look for this mass range, where dark matter is of a specific kind and has some specific interactions. And so you know what the final products of those three types of experiments are. How do you make up another lamppost? For example, how do you make up a lamppost that is like over here? That is what model builders do. They come up with theories of dark matter, and they predict what the interactions of dark matter is with standard model particles and how to observe these interactions. So composite dark matter is a new lamppost. And what I want you to understand out of all this discussion is that it is not a crazy model of dark matter. It is actually a very natural model of dark matter. And in order to explain that, I have to go back to the Standard Model. You are probably familiar with the Standard Model, but if you are not, just remember these two things. You have Standard Model particles with charges and masses, okay? And the charges are dictated by the symmetry group of the Standard Model, which is a gauge symmetry group, which you can write down like this. This is the electromagnetic force. This is the weak nuclear force. And this is the strong nuclear force. Okay? So this is what binds together the quarks and the gluons into protons and neutrons. This is, for example, beta decay processes. And this is light, the photon. Okay. Now, what do you know about the masses of these particles? Well, in the Standard Model, everything around us, 99% of the mass comes from the proton and the neutrons. Okay, that are bind together in the nuclei. So 99% of the mass comes from here. Is that telling you something? Maybe the other percentage of mass in the universe that we don't know about comes from something very similar to this. And this is what composite dark matter usually means. You have an extra group here where you have a dark force. And then this is going to be the dark matter mass. The dark matter mass is going to come from this new symmetry group, new gauge sector in mathematical terms. Okay. And then you can have your favorite model with some interactions to the other groups, depending on how you write down your equations. So composite dark matter is a new form of bound states, like a dark neutron or a dark proton. Okay. There is a new dark force that binds together some new dark quarks, like in QCD, and creates a dark matter candidate. How much time do I have?
Well, you already ran out of time, I guess.
Oh, you should stop me. I can go on and on with
well,
this.
I can't ask a question, so.
Okay, so one more thing in terms of where we stand in the lamppost. The mass of the proton is not fixed by any parameter that you can tune in your QCD theory. It comes out to be what it is because of the dynamics of the theory. Similarly, in this type of composite dark matter, the mass of dark matter is not something that you can control. It can be anything in this range here. And depending on how big this is, you will have specific signals in colliders experiments, in indirect detection, and in direct detection experiments. So if you observe something in these experiments, then you can fix the mass and understand what is the model of dark matter that best describes those experimental results. Thank you.
Couple of quick questions.
Yeah, so this dark force that you introduced, is it independently motivated by some particle physics considerations? Or?
It's, I think, to me, the best motivation is naturalness. It is a natural choice to have a dark matter mass that can be anything. So it's not restricted by some other experiments.
I'm saying that traditional sort of candidates like WIMPs,
yes.
I mean, one attractive point is that there are motivated purely by particle physics consideration, supersymmetry, whatever, and then they turn out also that they might also explain dark matter, and that's the kind of they kill two birds with one stone.
In this case,
is
no.
it motivated by dark matter?
It's motivated by this lamppost story. If you ignore this composite dark matter, if you actually don't think about this type of models, then you're losing an opportunity to look for dark matter. If you only focus on wings, and you only build experiment for wings, and you're not finding wings, then what is it? Yeah. This is the motivation, but some models of composite dark matter can be relevant for beyond standard model physics in the Higgs sector, where the Higgs particle is composite as well. So there are models that can incorporate both the Higgs sector and the dark matter sector as composite sectors.
Okay, so other questions?
If you introduce this large gate group, for example, then in the early universe, for example, you have many particles, you confine particles, and that
Yes.
affect the expansion of the universe and so on and so forth. So you have some constraint.
Yes, they are not very strong constraints. But at the beginning of the universe, depending on where or what time this sector confines, you can have different signatures. Yes. So that is actually a way to probe these dark sectors. For example, through this deconfinement phase transition. If the phase transition is a first order phase transition, it can generate gravitational waves. So you can observe those gravitational waves with the detectors today or in the future, and then find out what the temperature of deconfinement of this dark sector is. And that will set the scale of the dark matter mass.
Okay, so then let's thank the Enrico again and wish him good luck.